Hello and welcome to a new era of retrieval-augmented generation. Today, we are diving into the world of GraphRAG, a revolutionary approach that extends beyond the conventional to enhance how we interact with large datasets. Graph Retrieval-Augmented Generation is a sophisticated system designed by Microsoft Research over the last 1.5 years. They have been showing glimpses of their work here and there through research papers and blogs. But just last week, they completely open sourced the whole code, and I have gotten the chance to try it and ran a couple of use cases on it, and I can justify that it is completely groundbreaking. At the very base, it transforms raw data. The highest value comes from unstructured data. It converts it into structured or semi-structured, navigable, and highly informative knowledge graphs. It completely redefines the capabilities of traditional retrieval systems, as we have seen over the last 1.5 years. That such an incremental increase in RAG systems have come in. But what it does differently is structure those unstructured data into hierarchies and communities. So this makes it, as we'll see further in the video, it makes it not just searchable, but truly understandable. I'll be honest with you, this isn't just an incremental improvement. I see it as a complete overhaul of how we approach questions that require deep contextual insights from various amounts of information. So stay tuned as we explore how GraphRAG addresses the limitations of traditional RAG systems. So imagine that you're working with complex data set, like I have chosen the use case of analyzing Y Combinator companies, specifically in the AI domain, where they have invested in the last 4 years. So it's a snapshot of around 4,000 companies in which we have the company name description, long description, batch status, tags, location, country, year founded, number of founders, and their names. So it goes for 4 to 5,000 companies, and we have this sort of data for them. Now, traditional RAG systems will be able to answer this, ingest this, but to what capacity? That's the idea here, that we explore the capabilities of GraphRAG by defining a few questions. We just leave the usual notion of semantic search and we go a bit beyond. We go a bit abstract into understanding that does the system have complete holistic understanding of the data? Can it interconnect components from different portions of the data set or just complete different data points, such as a PDF file which contains a product description and the marketing and the finance documents, which are just completely somewhere else and doesn't even mention the product, right? So for this discussion, I have picked up 3 example questions. So let's go through them. How did the AI landscape change in the last 4 years for YC? Now, this is an abstract question, right? It needs an understanding of all the different components. You could easily say that I can just feed all of the CSV file or any other file into a language model like GPT-4, which has large enough context window. And you're absolutely right. For a file size like this, it is possible. Let's imagine at the scale of LinkedIn or Crunchbase, where the columns and the rows just go exponentially larger. And it makes a lot of sense and a lot of value to actually make sense of all of that data. And this is where GraphRAG comes in, that we move away from semantic search and having complete holistic understanding of the whole data set. Just an overview, what does the traditional RAG system struggle with? Contextual depth and scalability in evolving data sets. So quickly looking at the answers to a couple of questions. Which companies seem to be the most ambitious in their idea and value proposition? What does it need to have? It needs to have full understanding of the company's every company needs to understand ambition and the idea and value proposition. Now, if you think about it, it requires to certain degree reasoning, and that's what we have been trying to solve with agents. We have been making incremental improvements towards agents. But at the end of the day, for big data sets, agents also rely on RAG systems, if the context window is exceeded, of course. On the other hand, without even chain of thought prompting or other reasoning techniques, we still have very tangible results. You can easily see that it understands the umbrella under which the companies operate: healthcare, AI and machine pioneers, financial, energy, and environmental solutions. It says that this company is working on autonomous robots aiming to revolutionize surgery with significant advancements in medical technology. I don't know of many YC companies who are doing anything that is more ambitious than this. Same goes for AI and machine learning to democratize advanced AI technologies and impacting various sectors. So democratization makes it more ambitious, I guess. Fintech, debt as a service, revolutionized lending in the field fintech sector with a significant customer pipeline, including Uber. Another one. How did the AI landscape change in the last 4 years for YC? So typically, to answer a question like this, you would need a business analyst or data analyst to completely understand the data and maybe run some data analysis and some statistical methods to understand the trajectory of the market. So we have GraphRAG. It fully understands the data and it gives you a very nice holistic answer. And it completely reflects how the market trend has moved as well. Broadening of AI applications. IC companies have showcased significant innovations in AI across a wide range of sectors, specialized AI innovations. It notices somewhere, I read it previously, about LLMs and some computer vision technology, which has come in since 2020 to 2024. It's amazing to see that. It also notices that there's more geographical diversity in strategic locations coming up, such as New York, Bangalore, Los Angeles, I believe, and many others. So by the end of this video, or maybe the next one, we'll visualize the knowledge graph created and how big a value it provides in understanding that how the landscape has changed is also directly proportional to geographic diversity. And the fact that this RAG system, essentially a RAG system, is able to identify and understand it. So what is the secret sauce of GraphRAG? Single word: community. In the landscape of knowledge graphs, it introduces a game-changing feature: how to do community construction. So there have been a couple of papers about community construction, but none have applied it in this context. So what is it? It's not just about binding connections, that is, binding one person to another or maybe one entity to another. It's about understanding and organizing them in ways that reveal deeper insights which are not apparently visible. So community construction is at heart what makes RAG so effective, right? The algorithmic sense, the algorithmic answer is it's a clustering algorithm which identifies and groups related entities based on their interactions and common attributes. That's where LLM plays in. You have to understand that the related entities based on interactions and common attributes. Bigger language models like GPT-4 are excellent in doing this if you feed them a good prompt, the right context size, and just general understanding of what we're trying to do, right? So how it works? It works in 3 steps. First, we do entity detection, in which the GraphRAG scans the dataset to identify and categorize those entities. Next is relationship mapping. It then examines the connections between these entities, mapping out the relations that bound them. How does 2 entities relate to one another? That's what we call relationship mapping. Community clustering. So using techniques like the Leiden algorithm. We'll go in detail in the next video about the clustering algorithms and why Leiden was chosen, if I'm pronunciating it right. GraphRAG groups these entities into communities, which are clusters that represent closely knit clusters of related information, right? Each community tells a story. I was fascinated by seeing the results that what is a community? A community could be San Francisco is a community. A group of founders relating to a certain ethnic background is a community. A group of companies who are working in a certain space, operational in certain space is a community. So, and they're not isolated communities. They have interlinked, they have interconnections between them. What it does is if you have enough of those clusters and if you relate to them with one relationship or another, then you have complete jumping understanding of what part of the data, how one part of the data relates to the any other part of the data. And when I say data, let's try to visualize a graph here. So this community understanding is what allows GraphRAG to transform this chaotic data into organized, accessible knowledge. What we are going to see today, I would like to go into two parts, the indexing, which is an end-to-end knowledge graph creation pipeline, and querying. How do we perform and what are the various techniques to perform querying over this created knowledge graph? We have two, global search and local search. We'll go through them. So all of this is assisted through LLMs, and in this case, assisted through GPT-4 Turbo, at least in my experiment, but the code does allow you to not out of the box, but you can modify it to include open source models as well. Quick break. So the pipeline of indexing, I divided it into 5 steps, and that's what the blog that Microsoft released also mentions it that way. So it's quite diverse in the components that are involved, but we'll take it one step at a time, and it will be quite easy to understand. Starting with phase 1, or maybe actually let's go through each phase one by one. In phase 1, we compose text units. In phase 2, we perform graph extractions. Phase 3, we augment that received graph. In phase 4, we do community summarization. And in phase 5, we do document processing. Overall, doesn't make sense, but it will in just 5 minutes. So composing text utils. What is a text util? Text util is a chunk. In this initial step, we'll set a stage for how we approach large-scale text analysis and knowledge graph creation. And this will be done using the example of analyzing Y Combinator companies. As I said, text units are essentially chunks of texts which are carved from a much larger document. There's nothing unique about this. This is exactly how we have been doing it in any RAG systems. But still, as a refresher, let's quickly talk about it. So as most of us are aware, the creation of chunk involves the decision-making process on the granularity of text chunks. For our startup analysis, the chunk size is set to 200 tokens. So this granularity helps in capturing enough details about the company profiles without losing the context, which is quite important for accurate entity and relationship extractions, because that's what the basis of GraphRAG comes out to. But it's also essential to balance the chunk size as larger chunks while facilitating faster processing times, because you don't have to retrieve that many and might just find the right answer. It might lead to lower fidelity outputs, right? And less meaningful reference text as well. Conversely, smaller chunks, specifically in the context of GraphRAG, they tend to preserve higher quality and completeness. So by default, the GraphRAG system aligns chunks to the document boundaries that the line, which ensures that there is a one-to-many relationship between the documents and the chunks. So, which means that for one chunk, it will just be one document, and there will not be low overlap between multiple documents, right? It's a bit flexible. You can adjust it to many relationships if you want to capture more interconnected content. Um, but because for this use case at least, we just have one document source, that is completely fine to have one-to-many relationships. So I would like us to take a look at the output that is generated. So going down a little bit, it's very simple. On the left, we have the chunks. Nothing interesting here, to be honest. We have a chunk piece, which is of 200 tokens, as we already decided for it to be, and so on and so forth. So at this stage, the output comes out to be text chunks. We take this output and we move on to phase two, which is graph extraction. This is the very first important, or maybe the cornerstone in construction of a knowledge graph. So it converts this raw text into a more structured queryable graph that encapsulates entities, relationships, and claims. Let's break down each critical step in this phase. It begins with text units from phase one. So we take this in, we employ LLMs and prompts, which are smart enough to dissect these units and extract and categorize crucial elements that form the building blocks of a knowledge graph, right? We are moving towards how we are extracting entities and relationships, right? So it's not just about data extraction, it's about laying the groundwork for a network of interconnected information. Extracting entities and extracting relationships. So as I said, each text unit goes into a detailed analysis to extract these two components. These relationships connect these entities and are defined by their source, target, and the nature of the link. For instance, in our Y Combinator use case analysis, entities like startup companies and attributes such as number of founders and incorporation years are extracted. Relationships between them will be funded by, partnered with, etc., etc. So we identify the more important unique components, call them entities, and then we understand how they are related to one another. But because we need to have more concise and succinct understanding of the data set so that it can be retrieved and understood at a later point, we move on to summarization. So the descriptions gathered for entities and relationships are distilled into a single concise description. So this is quite validated to consolidate this information, making it easier for end users to grasp this complex data. Another part which leads from the entity extraction is extracting claims. So it happens simultaneously. Claims, what is a claim? A claim is a factual statement which is associated with those entities. Often these contains more temporal or conditional details. So you need to continuously evolve the knowledge graph as well as more and more information comes in. And that's where this plays a very huge part, that it adds a layer of depth to our graph. It makes it more temporally understandable and editable as well. So we call this claims as covariates in the research paper and responsible for enriching the context within the graph. So the consolidated outputs are nomenclaturally and taxonomically called graph tables. And let's take a look at what these entities and relationships look like. So these are phase two outputs. This is what the final entity snapshot data looks like. We have identified the name, the type, automatically, which is usually in knowledge graph world, it's more done through a schema, which is you provide the schema, you define it beforehand, and then you structure your data according to that schema. So this type is a node type, And accordingly, you have the values for it, you have the description for it, what it exactly is, a bit more expanded. You embed that graph embedding, which is basically just the description embedding and the name at this point. Um, and then you have the associated text unit IDs, which is basically pointing to your text utils. Similarly, for relationships, you have the source, which means there's one node source and then there's another node target, K-scale labs and Benjamin Bolt. So there's a weight between them and the description on how those two are connected. Again, text unit IDs, given readable IDs, source degree, we'll come to this at a later point, target degree, and rank. So the important part here to understand source, target, and how they are related. So this forms our entity and relationship extraction. Let's get back to it. What do we get out of this? We get out of this graph tables, and we move on to the exciting part, which we have been discussing for quite a long time now, um, community detection. The first step in this phase uses hierarchical lighting algorithm, which is essentially, as it says, it's a hierarchical clustering algorithm, which we'll cover at a later point. This method, in short, applies recursive clustering to the graph based on the strength of connection between each nodes. As we saw in the previous output, there was a weight, and this is what is used as the strength signal to perform this recursive clustering. And we continue to do this recursion until there is a community size threshold that is reached, which means there are enough nodes in the community which meets the community threshold, which is of course configurable. So this technique allows us to discern the intricate community structure of a graph. It makes it much more modular for these communities to exist. And it's very much essential for navigating and summarizing the graph at different levels of granularity. So at this point, imagine a bottom to top, bottom to top hierarchical understanding that is continuing to build. And that's what we are calling community. That at the very base, you start with a node, you start with another node, those two connect together, and then they connect with other nodes as well. We decide a number, n of these nodes together, and they form a cluster. So at this point, we understand what goes in the cluster, and we call it a community. We have n number of communities together, we bring them together, and we move on to a granularity level plus one. And then we understand what happens at that level. So when you do it for a large amount of data, you have that gradual hierarchical understanding, which goes at all the granular levels. What does it do for us? That's such a fascinating thing to understand, that having this granular understanding gives you the freedom that whenever a user or the person at the end is asking a query, it simply gives you the freedom to understand what the granularity of that query should be, right? It can be a very broad abstract question. It can be specific to some node information, some entity information. And you can decide on the granularity, you can jump in, you can extract that sort of condensed information required to answer that query. And this is quite unique to how we usually go, right? We don't have this sort of incremental understanding of the whole bird's eye view at the very top. So this is what makes graph unique: community detection and keeping it all holistically together. If you think about it in the back of your mind, this is a lot of tokens. This is a lot of summarization. This is a lot of entity and relationship establishment. So it is expensive. We'll eventually start seeing. I did some experiments myself in how much, let's say, yeah, financially, how much amount is being spent on this. I would still say that this is much lesser than what agentic frameworks makes you spend, especially with the bigger language models. And if you want to answer questions which needs reasoning induction, but still, it's quite expensive than the normal RAG systems. Anyways, that's a different topic. And here we are talking about community detection. We understand and will better understand how this clustering is done. Moving on to embeddings. So we follow the detection of communities and we proceed to graph embeddings. We use the node-to-vec algorithm, and this step transforms a graph into a geometric space. This is where the graph actually takes a graphical sense from a more structured or tabular form to a more geometrical space where each node's position is determined not just by its explicit connections, right? That's how we imagine graph to be, but also by its contextual similarities to other nodes, right? So it's not just that the connection is established and it's all good. Um, that's what makes it flexible to grow as newer data comes in. It will contextually adjust itself to a newer form of the graph as more and more data starts coming in. And this embedding process is quite crucial as it provides an implicit structure to a graph. We're not explicitly defining it. That's what will be when you define a schema. We're implicitly structuring the graph according to let's say the semantic similarity of the data around it. So, but at very different levels. So graph embeddings effectively capture the nuanced relationships between these entities, which might not be, of course, explicitly outlined in the data. So this enhances graph's utility by a lot, allows for a more intuitive and accurate query response based on concept similarities. The output of this is graph tables, which is essentially a tabular form of representing the embedded space of the graph. Phase 4. What is phase 4? Phase 4 is community summarization. As we touched upon just now, this is a lot of tokens. This is a lot of text being moved around. So it would be better for querying if it's more concise, if it's more information dense and smaller in size. So that's where this community summarization and reports comes in. So we at the start we harness this structured graph we previously obtained, and we enrich we take this enriched node-to-vec embeddings and hierarchy of communities, and we create comprehensive reports for each communities. Well, like, what is a report? These reports are understanding what actually goes in the graph structure, and if there is a cluster, if there's a community, and there is, as we said, there's n number of nodes in it, and how is one node connected to another is very information and text dense. Let's combine it all together and write one important piece of information, which can then be consulted in the querying process. So it's a two-step phase. The number one is we summarize the reports and we synthesize summaries that capture the unique characteristics and key data points for each community. So it's more like an executive summary. It contains the most critical information about the entities, relationships, and claims that define each community. But if you can think about it, not all communities are the same. So the depth of this summarization and the components that goes in it depends on the community's level within the hierarchy. So it 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 provides broad overview to specific detailed analysis. Is the essence of it. So following the generation of these comprehensive community reports, we further condense this information into summarized forms, and it directly distills this full report into more concise documents that retain the essential information. These reports are then embedded, and it makes it easier to process it. It makes it easier to vectorize it, therefore makes it easier to query it. And that's what the community summarization step moves us towards. The phase 5, which is document processing. So it's a unique one, as you might see that Okay, we don't have the arrow for it, but the documents from phase 1 and 4 combined together. The phase 1 documents, which was text tuples, text chunks, are coming back now in the last phase. Why are they coming back? They are coming back so that there can be a direct linkage from so much information dense community summarization and graph embeddings that we have created. How do they actually link to we need the certainty and this deterministic link back to the original text, right? So this is where this link to text unit comes from. Um, it's quite a critical phase because it maintains a traceable path between the document, the original documents, and the atomic units of analysis that we have done. For example, um, the use case that we have been following, there's a detailing, there's a document which details the Dropbox company, and we would want to link it back to text units because the text unit contains the funding information, technological innovations, and market impact, etc. So this ensures that there's enough insights and data received so that we can accurately trace it back to its original source. So I guess yeah, that's essentially explains it. So once we have this sort of linkage together, we perform embeddings over the whole document and transform into a vector switch, which can then be again queried. So this is what the KG indexing, the knowledge graph indexing, or the knowledge graph creation pipeline looks like. At the end, the output, I would like to show one instance of this output, as you might see that let's look at one community number 586 in our retrieve dataset. It contains information about Resonance, which is probably a company, and its founders who are working in San Francisco, associated with Resonance, so and so. They're about their work, about San Francisco as a strategic hub, the level 3. There are different levels to communities, as we said. This lies on level 3. Um, I'm sorry, I forgot what ranking was. Gives it a title. It gives the rank explanation. The impact severity rating is relatively high. As I remember that the rankings were 7.5 and 8.5, so I'll go and look at it again. It gives a summary, an extensive summary of what this community is and how are the different entities related to one another. So there are a lot of communities which gets formed based on everything that we just saw, which at essence is semantic similarity. So moving on from indexing, let's go to the part 2, which is querying. So I would like us to start with the global search. Global search is very interesting. It's what makes GraphRAG unique and apart from the vanilla ones. So before we move into the details, what is a global search? Global search, as the name suggests, it tackles broad questions like what are the top themes in this data? It traverses the full graph structure, right? So it doesn't really just hit one or n number of entities and then get information from it. It actually traverses the full graph structure, understanding which community clusters and their relationships that will be valuable to it. And while doing this, overarching concepts and patterns emerge. And when you go deeper from a top-down or a bottom-up approach into identifying the community and cluster, during this, you might be operating at many different levels and therefore be able to answer a more broader answer as well as a deeper answer. So it's sort of a combination of both. Um, the implementation. The implementation is a MapReduce style algorithms, which we will see in a second. So it starts with a user query. You can also have conversation history if it's available. And the very first step is a community selection, as we said, the cluster identification and community segments. So we shuffle all of these together, and for just to introduce some randomness and not to have bias towards maybe one community which has higher number of nodes and data in it. And also maybe if it's more directly related to query, it might give it more weightage, but we want a more holistic answer. So therefore, it should be possible for it to look at different communities equally. Um, we generate community reports and intermediate responses. So these shuffled community reports goes in, they get processed, which are essentially at the end of the day data chunks. We generate some potential responses. Let's say we generate these n responses coming out of each community, and we give it a rating. So we have a rating criteria defined in our prompts, and we prioritize these high quality chunks. This is the rated intermediate responses. Out of the n, we have 1 to n, which are scored and weighted. Um, Based on this, we come to the reduce stage. The previous one is what we call the map stage. We're mapping the inputs to the more relevant categorization with respect, not categorization, ranking with respect to the scores that I've received. The second is the reduce, at which the highest rated responses are ranked in filters, therefore organizing this data by its relevance to the query. So these top responses, um, we can configurably determine this. Let's say the top M responses are ranked and filters and are sent in to perform the final formatting, the final response generations, and output delivery. So as you see, this is a bit unique approach in how we process information on different levels. So this is what the unique thing about global search is. It mixes and matches information from various different density sources, shuffles them together to perform and find the right, more diverse answer, which is able to connect different points in a big data set. So um, yeah, this will be about global search. Moving on to local search. Local search is somewhat theoretically familiar. It's still different. Just the very base of it might you might see that this is what we are aware of. So it starts again with user query and conversation history. The very first step, this is the unique one, we do entity description embedding. So upon receiving a query, the system identifies keywords and phrases and convert these into entity description embedding. This embedding represents the essence of the query. How does it do it? It does it in a form that the system can process it further. What does it mean? It means that it embeds it. So using this embedded query description, the system scans through the knowledge graph to pinpoint exact entities, more than one, that closely aligns with the query. So as it could be a semantic search, it could be a hybrid search or a keyword search. Of course, in this case, it's a semantic search, but we can also think of it as a hybrid search at one point. Um, so in our use case context, this might include identifying some specific companies or maybe technologies mentioned by the user's input. So the next step is we map and extract across different data flows. So once these these entities are identified, the system extend its reach by mapping these entities to various data points. So you have one to one relationship or one to n relationship between the query entities to, let's say, one to n here for simplicity, between the query entity and the entities identified by graph. So you then go and batch the text units, the community reports, the entity relationships, and covariate data. So the amazing thing about this is there is a lot of variety in which you can do relevance understanding. So in most traditional RAG systems, you would simply, if we were to do re-ranking or relevance understanding, it would be through in the most vanilla fashion. In the most vanilla fashion, it would be through just the query embedding and what we retrieve from the sources. We can make it fancier by creating different variations of the query as well, and so on and so forth. But here we have much more sophisticated ways of doing it through text units, report, entity relationships, and entity relationships and entity relationships. Oh, yeah, yeah, relationships, um, and entity covariate relationships. There's a typo here. So among all of this, there is ranking plus filtering, because this is, as I said, this is a 1:n mapping. So among then there is prioritized text units, prioritized community reports, and so on. All of those together goes nicely into the prompt to generate a very well-structured response out of the local search. And this is also a very powerful way which identifies deep interconnected data within the GraphRAG system. So I hope you have a much clearer understanding of what GraphRAG is, what is the unique identification, and what is the USP that it provides us. I'll keep it short, or not so short, but just the theoretical aspects in this video. In the immediate next video, we will do a code walkthrough and we'll run the use case of Y Combinator company datasets and perform a lot of queries as well. And the direct correlation will be understanding whether how well this performs will be if we compare different RAG systems and their outputs, and then set a benchmark evaluation for how good GraphRAG performs both in its local search and global search. One small request, I'm starting new in videos and YouTube and giving information out in this form of content. So any feedback or any comments that you might have, I will highly appreciate it so that I can improve in creating better content going forward. Hope you enjoyed it. See you next time. Thanks.